All right. Okay, so if we have this chemical reaction, and that they tell us that NO, the rate of NO, I guess, I should say, rate of NO is equal to 0.066 molar per second. Okay, so they tell us during the reaction there's a rate of this for NO. At what rate is NO2 being formed? Okay, so what is the rate of NO2 in this reaction? Okay, so this is what we want to answer. So we can answer this question because of the stoichiometric relationships between these molecules. Okay, so the rate of NO2 is determined by minus 1/2 the rate of NO equals 1/2 the rate of NO2. Or basically they equal each other, essentially, right? Because the disappearance, 1/2 the disappearance, that's how we write it stoichiometrically. Remember how we would write those? If it was for O2, then we would write it differently. Let's see, I think they asked.
So then why did you choose negative 1/2?
Why did I choose it?
Right.
Okay, so see how the coefficient is 2? So if I'm going to write the rate stoichiometry here, I need to say 1/2. Okay, and I say the disappearance of 1/2 of this is equal to 1/2 the rate of NO2. We know the rate of this, that's going to tell us the rate of this.
So it's 1/2 because there's the coefficient of 2 in front of both, right?
Yes.
Okay.
That's exactly why.
If you were doing O2 to NO2, it would be just the negative rate of O.
Okay, and that's the other one they want us to do. So what is, so negative 1/2 the rate of NO is equal to the rate of O2. So here they're equal because they have the same coefficient. If it was a coefficient of 3 or anything of that nature, then we would use 1/3. Okay, if it was 4, we'd use 1/4. Okay, to determine these. So here, the rate of NO, so minus 1/2 the rate of NO, okay, is going to be equal to O2. And we were told the rate of NO is 0.066 molarity per second. And that's going to equal the rate of O2. Okay, so basically that divided by 2. And it is negative. Okay. So what are you guys getting for the rate of O2? Okay, 0.033, right? And it should be negative because it's disappearing, right? We're getting... oh wait, this should be a negative also, the negative rate of O2 because it's a disappearance. So we would describe the rate in a positive term. because it's the negative rate of O2.
Oh, this is a reactant.
This should be negative because O2 is also a reactant. Right. So they're both reactants. Okay. Okay, let's try another one. Okay, let's see. Okay. So the rate law for NH4 plus aqueous plus NO2 minus aqueous produces N2 gas plus 2H2O liquid. Okay. Is rate equals K times NH4 positive times NO2 minus, and this is so at 25 degrees Celsius, the rate constant K equals 3.0 times 10 to the negative 4 per molar seconds. So calculate the rate of the reaction if NH4 positive concentration equals 0.26 molar and the concentration of NO2 minus equals 0.080 molar. Okay, so that should be fairly straightforward. Okay, so put that all in. Tell me what the rate should be. What is the rate of that reaction?
Could you explain this? I'm still trying to.
Sure. Okay, so this is the rate law. Okay, what is the order of this? They told us that it's first order, right? Or else they would have an exponent. Here's first order, so overall this is second order rate equation. Okay. So if I'm going to solve for the rate of this reaction, they told me what K is. It's 3.0 times 10 to the negative 4, and they told me the concentration of each of these: 0.26 molar and 0.080 molar. You just put all those numbers together, multiply them, and you'll find your answer. That'll equal the rate. If I know the rate constant, I can change these to be anything, and I will know the rate at different concentrations.
And how do you know it's second order again?
Because if I add up the exponents here, 1 plus 1 is second order. If it was 1 first order here and second order here, then it would be a third order reaction. Okay, so what are you guys getting for the rate? Okay, so rate equals 6.2 times 10 to the negative 6. Is that what you're finding? And it should be molar seconds. Okay, is anybody not getting that? Okay. That should be a pretty basic, that's as easy as it gets, let me just say, okay? All right.
What would the difference be if it was
If
a third order?
it was third order,
So you just.
then this would be squared, and so that term right there, 0.008, would be squared.
Okay, so the rate law doesn't change for the order reactions. That was just, what was the
What do you mean the rate law?
natural log and 1 over, what was that, is that just some graphs?
Oh, when you're trying to determine the change in concentration?
No, that's the first order. The first order has a different formula for it than the second order does.
Right.
So the equation that we have here is the second order equation, whereas if it was just a first order equation, that's just the natural law.
So the rate formula changes?
No, this
No.
doesn't.
Okay. It would
This,
just be squared.
it doesn't matter, yes, the only thing that changes are the exponents.
For finding rate.
Uh-huh.
Okay.
With this, with the rate law here.
With rate.
Okay, so with this rate law, the only thing that changed are the exponents. But when we're looking at first order or second order reactions, then we do have different equations for changes in concentration versus time. And we'll do a few of those as well. Okay. Here's another one. So you have a reaction A plus B forms product. Okay. And you have this table of information. Concentration of A in molarity. Concentration of B in molarity. And the rate in molarity time per seconds. Okay, 1.5, 1.5, 3.0, 1.5, 2.5, 1.5. Rate is 3.2 times 10 to the negative 1, 3.2 times 10 to the negative 1, and 6.4 times 10 to the negative 1. Okay, so from this data, calculate the rate constant. Okay, what is the rate constant? So I want to solve for K. So let's first write a general rate law, okay, for this. Rate equals concentration of A times the concentration, forgot my K, okay, my constant times A times B. What am I missing? The orders. But I don't know them yet. That's why I have this data. So from the data, I need to find the orders here. Okay? So find the orders of those reactants. See blank faces. Yes, sir.
So A is double, right? 1.5.
Okay, so if I look at experiment 1 and 2, then B doubles. Okay? A is held constant, B doubles. I'm sorry, not doubles. It doesn't double. Okay, but it goes from 1.5 to 2.5. So let me make sure I wrote that down. Okay, but the rate stays the same. Okay? So what does that mean? It's zero order, right? So this is zero order. So I really would just leave it off. Rate.
That's B.
I'm sorry. It's zero order. Okay? So I can just leave B off because it doesn't change the rate. Increases in the concentration of B don't affect the rate of the reaction. Okay? Now, look at experiment A. Okay? From 1 to 3, B, it's held constant. Here it triples. And how does it affect the rate?
It doubles.
Okay? So, I'm sorry, it doubles. My math's not great. 1.5 to 3 it doubles, right? And there, the rate, it doubles. So what does that mean about the order? It's first order because it's the same, right? So 2 to the x equals 2. It has to be first order. If this doubled and the rate doubled, then what is the order? It's 2. What would the rate have become, or how, by what factor would it have increased if this order was 2? By a factor of 4, right? So that's how we determine the rates from here. So right here, this is the rate law. Now I want to solve for K. I want to solve for K, the rate constant. Okay, so do that. Tell me what the rate constant is. Okay, what are you guys finding for the rate constant? Okay. Okay, so 0.213 per seconds. First order. Is anybody not getting that? Okay. So, you can choose any of these, right? And they should all, with this data, they should all give you the exact same K. Well, not exactly the same, but relatively the same K. And if we're in the laboratory, we would actually find the K for all 3 of them, and then we'd get an average K, and that would be our best K. Okay? So that's what that's how we're going to calculate. Let's try another one of those.
From yesterday's example,
Yeah.
we did K equals the rate of the concentration of the rate over concentration of A over the concentration of B, or A and B on the bottom. How come we're only doing A on this one?
Oh, okay. So you see how B is zero order? So when we rewrite our rate law, rate equals K times just A, not B. So we left B off because it's zero order. So it doesn't affect the rate. Okay. So if it does affect the rate, we will include it. If it doesn't, we don't. Okay, let's try this one. Okay. This is my data. The question is, find the rate if X is 0.3 molar and Y is 0.4 molar, which is not one of these. Okay?
That's the starting point. What I need to use this data for is to figure out what are the orders actually. What you want to do is you want to come here and find where Y is one across the board. See how right here is 0.6. And right here X changes. So I can use this to determine order or right here, once again, I just do this one. So you do fine tune, and then for Y, I fine tune here there are actually for this one. And then how is that going to affect? What happens to the rate? Let's actually look at it. Get caught up. Let's say you got it done. So let's go from here to here. Say you got it done. So that means, so this is for X. So X was double. So 2 to the Y. So what happened to the rate? 0.25 to 1. Okay, so from 0.25 to 1. What happened? So double went from 0.25 to 0.5. It went to 1. Okay, so it's must be second order.
So it's basically saying if I'm
Well, there was this one X. Double it.
the reason so that is power of one because whatever this is doing, this does. If you put a splitter up there, if I dump with this, what would this do? This would be
Oh, well,
this would be power of two.
so it did the opposite. in that, it didn't really do the opposite.
That's why we always not do.
So you can go backwards then?
You can go this way, because if you're looking at what happens here versus here, double this double quadruple.
So when you look at this one, this one is not that is the same way.
Right, you find one that's held constant, and you look at what happens to the X. And from here to here it's double. Or it got cut in half if you look at the other two. Okay? But it doubled from here to here, so how did it affect the rate from here to here? Quadruple.
This is two, so you got two.
This, no.
So now we gotta look at the X that's on the bottom. So we know what this X is on. X is second order. So you put it to second.
So now we look at zero, then you just
Sure. Those two are held constant. What happens here? It goes from 0.3 to 0.6. Okay. What happens to the rate?
That's just what we're doing.
137. It doubles. It's first order because they're both the same. If this doubles, that's the first order. Okay. How did you find the rate? Be a great one.
That is.
No, I was showing that one, because I was like, when I first came in, I was doing the same thing that I was doing. It was like, you would know, oh, it's like 4 times the size, you put 4 times the size.
How strong the gravity are.
It's because it put 4 times up, and it's when we switch to, that's why it's a power 2. It's not, you don't put 4 down, just to solve for it and realize it's a power 2.
Okay, well, cause like I was.
So let's do it. So if I hold these two,
Well, I have to work on other
then
stuff.
I look
I
at
won't do
here,
it Friday.
0.2 to 0.2. What happens to the rate? Goes from 0.25 to 2.
Oh, really?
So, if this double, okay, and it quadruple, then what is equal? Excellent. Okay. Now let's look at another. Let's hold this one. Those are 0.3. What happens to the rate? 0.127. Okay, so if I double this, this doubles. First order.
Because I think that's only for, I think you're only supposed to look at the X's.
That's always hold one constant, that's fine. Okay, yeah, it's gonna have to be a.
So I guess we need to just.
Then you'll have to be able to put K into the original equation to solve for it at point.
I wonder why he used these two.
I'll have to double check it, but everything.
No, not next to each other, like, so you have to find another.
Start, right?
Well, choose 10.6 no matter which.
I just don't get why. Like, these are the two that I chose.
Overachiever.
Double. So like, I don't get why.
So what I need to do is I need to find. So let's start with you on 0.6. You would do proof of the K for each one. And here, for the K for each X, add all the rest. How much did it change?
What if happens to this one?
That's
So
what.
if you have to figure out K.
What happens to it?
Second order.
In this 0.25 to 1.
Figure out K.
Okay, we're gonna, okay, so.
This double, that's
And they should be,
It should be technically.
the same. Yeah. But remember, all of our experiments, this like, if we go out a little bit, and then this one happens here. It's actually going to go out just a little bit. The other ones, they don't have to have this very same one. This is a little bit of the accuracy. Just double this one.
Okay, so say you finish the so you look at how it
We did everything we needed to know.
Okay, so first try to write the rate rate equals concentration of X equal minus the concentration of Y.
I'm just trying to figure out
So do that. Let's get start with Y. Look at Y and find two experiments that are the same. Oh, 6.6. Okay, tell the constant. Now look at what happens in X. Let's go up 0.2 to 0.4. What is it?
Oh, so you don't look at this, you look at the
0.25 to 1.
So
What is that?
why?
That's for the act, right?
So that's why I asked.
Okay, okay,
In a section.
Okay, that, okay, essentially, but I was thinking.
You would assume it's quadratic.
Okay.
So 0.25 forward to 1. That's quadruple. So if it doubles, and the rate quadruples, what's the Y? To that Y equals 4 to the second. Square it.
Okay, that's what I was doing like two now, or I was, yeah.
Okay. So X is second order. What is Y? So let's find an X.
You mean Y second order?
No, Y. No, we figured out X.
No, you're.
We held Y constant.
Oh, okay, okay.
Now we gotta figure out Y. So we hold two experiments constant for X. Okay. So like 0.2 and 0.2. And look at what Y does. It goes from 0.3 to 0.6. From 0.3 to 0.6, what happens to the rate? Double. So you double the concentration.
that would be my.
No, once you have the orders, you're using those orders. Yeah.
So that's how I'm going to write.
You're gonna have X to the power of 2 to the 12.
Okay, so excellent. Rate equals concentration of X times the concentration of Y. X is second order, Y is first order. Whoops, I forgot my K. I always do that. Okay, so now I want to solve for K, right? K equals rate divided by X squared divided by Y. And then I can solve for K. So I just choose an experiment here. I choose one of these, and I can solve for K. The best way would be to solve for K for all of them, and then find the average K. What did you guys find for K? K equals what?
10.625.
Say it again.
10.625.
10.625. Okay. So 10.625, and rate has units of molarity per seconds, and each of these have this is molarity squared, and this is molarity. The molarities there will cancel, and we're left with per molarity squared seconds. It's a third order reaction, so that would be the units of it. Absolutely, for K. So if you were told K and it had these units, that would be an indication that this is a third order reaction. Right? Okay? All right. Now that I know my K, I can simply put it in to solve for the rate equals 10.625 per molarity time squared seconds times the concentration of 0.3 squared times the concentration of 0.4. Okay? And these are molar units, so those will cancel there, and I'll be left with per seconds. And what'd you guys find? 0.3825. Whoops, I need a this one actually didn't cancel, I'm sorry. Molarities per second will be a rate. So the molarity squares cancel, you're left with molarity per second, which is rate that you should be. Okay. All right. 0.308. Okay, let's try another one. Okay, let's try this. Okay. So I want to solve for the half-life, okay, of first order. And the equation for half-life is 0.693 over K. Okay, and I'm going to give you another equation for first order, the natural log of the concentration, the new concentration, I'm sorry, at the time is equal to the negative KT plus the natural log of the concentration, the initial concentration. Okay? So, how am I going to answer this question? If I find K, I can find my half-life easily, right? How am I going to find K? What's that?
So we gotta find the concentration of A. And then after 60 minutes.
Yeah, we know. Okay, so what was the initial concentration? Let's start there. How about, let's say, 100? Okay? So let's say A naught is 100 or 1. We could say 1. Either way, it doesn't matter. It's going to be a ratio in this. So 100 or 1. What is A at 60 minutes then?
75 or 25.
There you go. It's not 75. It's 25, right? Or 0.25. There you go. Now, I can leave this in minutes if I want. But that means my K will be, if I leave it in minutes, then my K is going to be per minute, okay? And normally, a lot of times we have it in seconds. So if you wanted to convert those minutes to seconds, you could, but you can leave it in minutes because half-lives can be determined in minutes. It's okay. A at the time, which is 60 minutes. So the A at 60 minutes is the final concentration at, essentially, yes.
It's okay, keep it in minutes.
Yeah, just go ahead and keep it in minutes.
So that is kind of like molarity per minute instead of percent for concentration.
For the rate, I guess if you were looking for a rate, it would be molarity per minutes. But if it's K, it's just going to be 1 unit per seconds, or per minute, I'm sorry, per minute. Because it's first order, so it'll be per minute.
Why is the number 0.693? Is there a reason?
Yes. It's the natural log of 2.
Natural log of 2?
Uh-huh. It's constant for the half-life of a first order reaction. Okay, did anybody find K yet? K equal to? Oh, you found the answer. Well, let's start with K. What did you find for K?
3.85 times 10 to the negative 4.
Oh, that's per seconds. Okay. So what is it in minutes?
0.0231.
2, oh. That's why I'm so good at chemistry, because I'm dyslexic. You have to be dyslexic to do chemistry. Okay, good. And then after that, it's a simple matter, right? 0.693 divided by either 3.85 times 10 to -4 to find your half-life in seconds, which would be kind of a big half-life, or you find it in minutes. Would you find it, if it's in seconds, what is it? 1800. Okay. If you're seconds, that's seconds. Okay. If your T1/2 is in minutes, it's 30 minutes. I'm sorry, say it again? Okay, let's go through it. All right. So here I want to solve for K, right? This is how I would recommend it. I would take, so I would take the natural log of 25 here is equal to your negative K. And here this is going to be 60 minutes for the time, plus the natural log of your initial concentration, which is 100. So I would simplify, the first thing I would do is simplify this term and this term. The natural log of 25 is what? 3.219. What is the natural log of 100?
4.605.
Say that again?
4.605.
Okay. So now I can take 3.219 and I can subtract 4.605 over here. 3.219 minus 4.605 equals negative K times 60 minutes. And then I could divide 60 over here, and that would equal my K. So negative K equals 3.219 minus 4.605 divided by 60. This is molar. Divided by 60 minutes. Okay, will give me my K.
Divide by negative 6 to get rid of negative.
I'm sorry?
Just divide by negative 60?
Yeah, you could divide by negative 6. Yeah, this is going to end up being a negative term, and then you can divide by negative, it gives you a positive. So K will be a positive term. All right? And once you find K, using that half-life equation should be simple. Let's put it in there. Say it again. Why is this 100? Okay, so let's look at the question. Okay. So what is the half-life of a compound if 75, so we're working in percentages, right? If 75%, they don't tell you how much it is. It could be any amount. They're just saying if 75% of it decomposes, okay? So we're just going to make the assumption it's 100 because it's a percent. Let's start at 100%. So we say 100. And over here we say 25 because that's the amount that is left after 75% decomposes. 75% of 100 decomposes. There's 25% of it left. Okay? Okay, now this time, instead of giving me the percentages at one time point and then the amount at another time point, they're giving me the half-life, okay, in seconds. And they're saying find the time required for 95% of phosphine to decompose. Okay? So let me actually write down. And it's first order again. So T1 half
So how do
equals,
you know if it's first order when it gives the equation?
how do we know what?
If it's a first order, if it just gives the equation.
Say it again, I'm sorry.
How do we know if it's a first order or second order when it just
Oh,
gives you the equation?
they tell you. They told me in the question, I just didn't write it. It's first order. Okay, first order. First order. So yeah, that's information you need, right? The T1 half here is 0.693. 0.693 divided by the K. Okay, and once again, we're going to use this same equation here where the natural log of the initial concentration, I'm sorry, not the initial, the natural log of A at the time is equal to the negative KT plus the natural log of A naught initial. This is kind of the same question, just backwards. Kind of the same question we just did, just kind of backwards.
We recommend putting it in seconds, minutes.
In this case, because it's in the T1 half is in seconds, I would leave it in seconds. Okay, unless you get a ginormous amount of seconds, and then you might want to convert it to minutes. So basically, your half-life, if your half-life, should be in years, you don't want to keep it in seconds. So, you would convert it to whatever's a reasonable amount. But since they gave us the half-life in seconds, it's probably reasonable to keep it in seconds, everything.
Pressure and all that, temperature and all that, constant, like atmospheres. I was thinking that the answer is specific minutes, seconds.
Yeah, you don't have to. You just have to make sure it's all the same. If it's in seconds, you keep everything in seconds. If it's in minutes, you keep everything in minutes.
So you're gonna solve for K, right? We get 17.5. This is what okay. So they tell you that the T1 half Okay, so 95%. So start with 100. And what's left? 5, 2. Is that? Oh, that'll be. Yeah. Oh, okay. That's good. Good. Let me. And what's your? Let me look at how you come. I did. Yeah.
It's like using 3.6935.
I went back and I had to go into make myself look good. So walking with talking, I literally went on rewrite the equation and write it. So I was like, okay. So, so once you plug K, you're gonna plug it into this bottom. You're gonna use the half-life equation. So if you do 151, K, you're gonna use it to solve for the time for T.
That's not the hill.
Yeah, I just solved.
So the half-life equation is 0.693. So if I solve for K, then it's.
That's not, you should use 100, it's easy. Yeah,
I'll just solve. But the problem is that you don't have the time. So what you're going to do is you're going to solve for K, but using the half-life equals, move K up to put the half-life down.
This is divided by time.
The half-life was 30 minutes. So this divided by that. If you use your half-life equation, any Euclidean, if you got a K and it's give you on this equation, this is good, 105. But instead of solving for K, you're solving for the same.
Whatever 95% is, that number is K. Whatever that number is, it's just a number. 95%. So well, if you wait, no, yeah, just make sure you get this number right.
Yeah, we don't have time.
Okay, John, I'm gonna show you. Don't solve. Wait, no, wait, what did you get? Point 019. Okay, we're gonna tell you what you want.
Then I can solve for the T.
And then it's this number 5 goes.
Yeah.
I try and wake up early, but I'll sleep all day. Usually, but I guess I'm not gonna.
Yeah, I use that.
I still got
Any
the.
number of roundings,
Oh.
give or take a couple of days. Yeah. So once you say like, if you're
They gave us a T.
Okay, so as you've mostly figured out, you need to solve for K using your half-life equation. So 0.693 divided by 35 seconds. once you have K, you're going to use that right here, and then you're going to solve for the time in this equation using A initial as either 1 or 100. And the A at the time would be 5 or 0.5 if you used 1. Okay? So that's what I'm going to do there. Okay? The time equals 151 approximate seconds. Okay? Is that what you guys are finding? Good. Okay, let's try two. Constant. Okay. How many seconds would it take for the concentration of NO2 to decrease from 0.62 molar to 0.28 molar? So, what equation do I need to use for this one? I need to use the second order, not the half-life, but just the change in concentration per time equation for a second order. Okay. So 1 over. Yes, let me just write this down. Okay, so I want to use this equation.
So it's the K.
On our exams, will we be given the equations or do we?
You'll have yes, you'll have a reference sheet.
Because there's an extra concentration.
Sorry.
You're okay.
That's not okay, don't let it happen again.
It was really loud, sorry.
Is that, what is that?
initial, so it's starting. The other side of the world, you know, it's like the A is 0, B is 0, that will be zero. So anytime you set that, no, is per molar sometimes, it's just you know, that is like the concentration.
Okay, did anybody find a time?
Yes, 3.63.
Okay. Okay, so 3.6 seconds is the time, all right? So I simply need to solve for this. I'll simplify this term, simplify that term, and it should be an easy matter. Subtract this from that one, and then solve for time and bring k over underneath. Okay? It's multiple choice, so there's not really a rounding factor. I'm not so concerned with significant figures and that thing so much with this class. If you can do this, if you can solve for that, that's wonderful. Okay, if you understand that. Okay, so don't spend too much time worrying about rounding. Just get your answer, find the closest. It's going to be the closest one. Okay, so let's go ahead and take a break.
Can you leave this up?
Yeah, I'll leave it up.
Okay.
Oh, yes, it says it in the question. Oh, I know how. I think I did that on purpose. It's because, look at your units on K. If it was first order, it would be just per seconds, but because it's second order, it's molarity per second, times seconds. If it was third order, it would be molarity squared times seconds. Okay, so essentially every time you increase the order, you're increasing the number, the molarity unit on the bottom.
So, what would zero order be? A zero order reaction?
What would a zero order reaction be?
Yeah, I mean, with the units.
There is no K for a zero order reaction. Is that what you're asking? There wouldn't be a. No, they're reference material. Or I guess essentially for zero order, the K would be the rate. They'd be equal. Because you would get rid of the molarity term for a zero order. So it would be So it would be, I guess it would be molarity time per second, the rate. Because you don't cancel out the molarity.
Because I look at it and I'm going.
Oh yeah, absolutely.
I'm like sitting there and it goes from natural logs to a -1. I'm like, that's an interesting trend that you see. I was like,
yeah, I mean if you
work backwards to some type of
yeah, these are
calculus-based
it's all calculus based. They're derived. Let's see, they usually show. So like for this one, I kind of go through.
Is it one of those things where these are all D's instead of? Okay, there it is. Yeah, I was like sitting there and I'm going, and it feels like they're just replacing it with, if we do a different order, then you're replacing it, and by replacing that exponent, you end up with
instead of natural log, you end up with -1, and -1 ends up being that inverse. And so I was like, that's interesting. That's definitely related to some starting calculus equation where they just changed the one
Oh, yeah,
thing.
these are all derived from calculus.
Oh, okay, it just continues there. Oh, this is. Yeah, there it is. Yeah, so once you throw the exponent up there, you integrate it, you're back down to the inverse.
Uncle said he saw a kid on a bike crash and he was like, that one.
Yes, ma'am.
Okay, so like I'm looking at the homework.
Yeah.
I didn't get like how do you when I ask you for like increase in the point, like I'm also like how do you actually determine it? Polarity, hydrogen bond,
Like the one with the hydrogen bond.
Except for something that's ionic. Ionic is higher than hydrogen bonding, but if it has hydrogen bonding, it's right. Ionic is the highest, but there's no ionic. Here's non-polar, non-polar, and then you have CH3OH and CH3. So this one has hydrogen bonding, this one doesn't.
So probably
By mass. So it means why is
And that's just your unit of time. So it's yeah, so you would divide it.
I did, but that's a good point. There's a lot of people that are.
yeah, I walked in.
Michelle? Isabella?
They have strong sulfur states.
Linda? April Lynn? Sean?
Sulfur states.
Nina?
Sulfur states.
Vice? Elias? For some reason, I always think it's either Lies or Leah's. You did it right. So maybe that. Leah's.
Did you check to see, or did you check me in this one? Because I know I had left like to use the restroom and she said that.
Yeah, what's the name?
William.
Jacqueline?
That's it. Late. Yeah, that was right.
Vapor pressure, when we did then we got yeah, low vapor pressure. This one has the most wood, was 8 to something, and then
I just signed up for both.
Oh, okay. Yeah, that one.
That was 13, 11, 11, 11.
It's cool. Like this is 14, 12.
yeah.
Okay, so in this question, if I get your guys' attention now, please. So we want to go, we're given this information. K1 is 4.60 times 10 negative 4 at 350 degrees Celsius. Okay, at K2, at a higher temperature, or at a different temperature, K2 is 8.8 times 10 to negative 4. So my rate constant has changed because my temperature changed. They don't tell me the second temperature. That's what they want me to solve for. What is the second temperature? Okay? So we want to solve for that second temperature. I think,
Did you give us the activation?
I'm sorry. EA equals 104 kilojoules per mole. All right, sorry about that. There you go.
Oh, it's a constant. And R is just R is a constant. And R is Oh.
EA can be determined experimentally, so they probably just determined it experimentally. They know the activation energy. But they want to find what was the time. Oh, and guys, look at your constant. What are the units of your constant? Joules per Kelvin.
What are you saying?
270.
No. 1 kilojoule. We're trying to find T2. No, we already have the one. One is T2.
No, but like
Yeah, they're the same.
So kilojoules would be less
Would you suggest converting, so either the joules or the kilojoules?
Activation energy.
I would recommend converting the
So you
kilojoules to
convert
joules
to
and leaving your constant as 8.314 joules.
You want to rather What did you do?
did you memorize?
It's simple, like 1 kilometer is like 1,000 meters or something like that.
No, did you memorize like these? Like,
Is that right? Or is it 1
You're right.
One over T2 is if it's
Yeah. No, I think it's T2 minus T1. Yes, you do. Has to be in Kelvin. I don't. Sorry.
So like on like Celsius and stuff, like when you're converting, you don't give us a conversion thing?
Not for Celsius to Kelvin, but it's 273.
Yeah, that. You don't give it to us on our test, we have to like.
I would expect you to know that one. Thanks. Yeah. The conversion between Celsius and Kelvin.
What are you talking about? Because you can't cancel something out if, wait, 661.
Yeah.
You can't cancel because.
Yeah.
No, because you're doing, subtraction on the top.
Not working?
You can't do that. If it was T1 times T2 on the top, then you could, but you can't.
Let's see. I probably have one on my phone, but you might have one on your phone. You guys could use this one as well. Okay, it was brought to my attention. If that one's simpler for you to use. Okay. Either way, you're gonna find the same answer.
The other one's too much crazy enough.
Did you guys find an answer?
643.8 Kelvin.
Okay. Yeah. I think that's right. Oops. I'm sorry? 643 point. I think it should be more around 643 or 644. Hey guys, that's what you should be getting to. Put it in Celsius. Go ahead. No, go ahead. What is it? 370 something in Celsius?
Plus 23, 370, 374.
Yeah, I got
Okay, let's go ahead for. If you guys are struggling, let's go ahead and simplify some of these. What did you guys find for the ratio, the natural log of this ratio of the k's? What was that? Negative. Say it louder. 0.65. Okay. And then, what did you guys? Did you multiply r over here? Is that what you did next? Did you find this EA over r? Is that what you did next? Okay. What's EA over r? 12.51. Okay. Times, and I'm just going to leave this whole.
Did you guys keep your kilojoules?
So it should be 12,000 probably.
Well, what we did is we did 104,000 divided by 8.314.
Right.
So that we did both in joules, and that's what we got.
That's 12.51?
Yep. Double check.
Yeah, that should be.
12,051.
Should be 12.5 on our.
Well, I won it? Okay, we
12,500.
set the decimals. Try again.
Okay. 12,519.
No, 0, so 10.
Okay, that's fine. Okay, and let's just leave this as an x term right now. And then you could solve x equals 0.65 over 12,510. Okay, anybody do that? I'm sorry, negative. Did anybody do that? What'd you get? .032. Whoa, what am I doing? Okay, good. So 0.032 will equal 1 over t minus 1 over t1. What is the reciprocal of the Kelvin temperature of T1? Equals 1 over T2 minus.
I don't think it's 0. That's not what it's. Yeah.
Oh,
It's 5.8
you guys are lying to me.
times 10 to the power of negative.
Say it again.
It's 5.18 times 10 to the power of negative 5.
Negative 5.
Yeah, negative 5.
Right, okay. Good, thank you. Okay, and that is going to equal 1 over T2 minus 1 over T1. And then you can simplify right here. Right? 1 over T1 is what? What was the Kelvin temperature at T1? 623?
Yes.
Okay, so the reciprocal of 623? Oops, minus 0.036? 16? Sorry guys, I'm half deaf. Okay? It's I have 5 kids and I can hardly hear, anything anymore. Negative 5.18 times 10 to the negative 5. And then I can add that term over here, right? So, negative 5.18 times 10 to the negative 5 plus 0.0016 will equal 1 over T2. Like that? Okay. Times T2 equals 1. And then T2 equals 1 over 0.0015. And then we should get...
Well, that answer is 666.
1 over 0.0015?
That was an awful lot of rounding up there, yeah.
Yeah, okay, that's why. So, but the algebra's same, 666?
666.
Okay.
So the answer is the mark of the beast.
If you do a lot of rounding, yes. Which then spells doom.
See what happens when you round?
Yeah.
When you round too much? It should be 644. But if you round, that's just devil worshiping, I guess. That's not as bad as the equation of life itself. The equation of life, energy in our bodies produced from glucose because it reacts with oxygen, produces carbon dioxide and water. 666. So, sorry guys, you're not going to scare me with those numbers. It's just not going to happen. All right.
Proof that sugar is bad for you.
Sugar is bad for you. That's not true.
Of course you will die.
Yes, you will. You will definitely die without it. Okay. That's enough of chapter 12. Okay, so hopefully you guys feel a little more comfortable with those equations and how to work things. Come the test, you should be experts, right? Okay. Next, we're going to talk about equilibrium. And what we do here is going to be the basis for like the next 3 chapters. So we got to get this down. Okay? We got to get this down really well because when we get into everything else that comes after it, it follows this. Okay? It's going to follow it. So chemical equilibrium is the state in which there is no more observable change in the concentration of the products and the reactants during the reaction. Okay? Now, there is a misconception that equilibrium means equal concentrations. Equal concentration of product and equal concentration of reactant. But that is very far from the truth. Okay? That is not what it means. It doesn't mean you have the same amount on each side of the reaction. It means that you have the rates equal. The rate of the forward reaction and the rate of the reverse reaction are the same. Okay? So when those two rates are equal, you have reached equilibrium. Reaching equilibrium does not mean I have just the same amount of product as I do reactant. Okay? I could have way more product than I do reactant and be at equilibrium. Because maybe the reverse rate is slow and the forward rate is quick. So I wouldn't have the same amounts on each side. But once I decrease the concentration of something enough to where it slows that reaction backwards down, then the rates become the same. Now I'm at equilibrium. Okay? So, now here, what is true is that once you reach equilibrium, the reactants and products remain constant, but that doesn't mean the reaction has stopped. The reaction hasn't stopped. It's just that you're going forward at the exact same speed as you're coming back. So the concentrations of those reactants and products will not change anymore. Okay, so here's an example of water of physical equilibrium going from liquid to gas. Okay, so water will vaporize and then it will condense. If you put water into come on. Why won't it go? If you put water into a cup and put a lid on it, let's say, okay. So here's my cup. Has a lid. It's at this It's at this volume. Okay. Then it will begin to evaporate and build up a vapor pressure above it. So initially it's only evaporating because there's nothing to condense. But once enough vapor builds up in there, it'll begin to condense back down into liquid. Okay? And once the rate of evaporation and the rate of condensation are equal, then the volume of this will not change anymore. It will remain constant. It'll be at equilibrium. Okay? That's when it will have reached its equilibrium state. Okay. So that's an example of a physical equilibrium. A chemical equilibrium, here's an example where you take N2O4, which decomposes into two NO2s. All right? And NO2 is brown, so it's colorful. You can see it. So you wouldn't see that color, but over time it would gain that color. And then this color would remain constant at some point. Okay? Even though you still have some N2O4 left because it's going back and forth at the same rate. Okay, so start with NO2. So here's that equilibrium. What happens if I start with NO2? Well, if I start with NO2, then it's going to make N2O4. As the concentration of NO2 decreases, the concentration of N2O4 is increasing. Okay? And now look, it has reached equilibrium when the concentrations are constant, not the same. So I don't have the same amount of NO2 as I do N2O4. It's just that I've reached equilibrium because the ratio of NO2 and N2O4 have reached a constant. Okay? So let me see if I can better explain that here. If I start with N2O4, okay, now look what happens. As the concentration of N2O4 is decreasing, the concentration of NO2 is increasing until they get constant. They have reached a constant state. That constant is an actual calculated number that you can calculate. And it will always be the same. It'll be the same for this ratio or for this ratio. The number that it equals will be the same. Okay? So we say it's the constant that it has reached. It has reached at equilibrium, the concentrations stay the same and equal, the ratio of them will equal an actual number for this reaction. It's called the equilibrium constant. Every reaction has its own equilibrium constant. Okay? And you can determine what that is. You can calculate what that is. Okay, if I put both NO2 and N2O4, then you get something like this. Okay, the NO2 is decreasing and the NO4 is increasing because it hadn't reached equilibrium yet because it was deficient in some N2O4. So it converts some of the NO2 into N2O4, and then it gets constant and it remains there. This ratio will equal the equilibrium constant. It will equal the equilibrium constant. Okay? Okay. So here we see some data where you have the concentration of NO2 and the concentration of N2O4. Initial concentrations. Okay, we didn't have any of this. We had some of that. And at equilibrium, this 0.67 decomposed into NO2. So 0.0547, if you take 0.643 plus 0.547, it's going to equal 0.670. These are the equilibrium concentrations. That's how much of it decomposed into NO2. Okay? It decomposed into that amount. Here is the ratio at equilibrium. Okay? Now what I want you to notice here is that if I take the ratio of NO2 over N2O4, you don't get a constant. But remember I told you it needs to be a constant? It needs to be constant. So what's missing? What's missing are the coefficients. Okay? What is the coefficient? Let's go back. Look at the reaction here. N2O4 has no coefficient. NO2 does. So remember when I told you with rate, you don't use the coefficients as your orders, but in equilibrium, you do? So NO2 needs to be squared. If I square NO2, now look. If I square NO2 and divide it by N2O4, the ratio here is now constant. Okay? Now I have a constant. If I take these, I square this one, and I leave this one first order, and I take the ratio of them, it will equal a constant number. Okay? That's equilibrium. Now we know it's reached equilibrium. Okay? That's why these experiments will remain constant at these points, because they have reached those equilibrium ratios that don't allow them to change concentrations anymore. Okay. So experimentally, we see that, let's just go back really quick. The equilibrium constant for this experiment is 4.65 times 10 negative 3. Okay? So let's see how we would write an equilibrium expression. They are written in this fashion. Okay? The equilibrium constant is equal to, I'm going to simplify it, products over reactants. Products are always on top. Products over reactants. In rate, we only deal with reactants. In equilibrium, products over reactants. Okay? And they will be raised to their coefficients. So here, for this experiment, we would write the rate expression. The equilibrium expression. I got to get off of rate. The equilibrium expression would be NO2 squared. Well, that's weird. And divided by the concentration of N2O4. Okay? And that would be my equilibrium expression for K.
If you have more than one, it would be add them?
Multiply them.
Okay.
Yep. You're going to multiply those together, and you're going to raise them to their coefficients. Okay, and we'll do some examples of that. So that's a good question. Okay, so that's going to equal my equilibrium constant that we found earlier in the experimental data. So here's a general equation for equilibrium. Okay, And this is what you'll be given on your reference material. Okay? You'll hardly need it after we're done here. I mean, you're going to do so much of this that it's just going to be irrelevant. But it'll be there. Okay? So this is a generalized equilibrium expression. The coefficient of C is the order I use for C. Okay? Etc. Okay. Yes, thank you. So, what does a K tell me if I'm given it? First, if your K is greater than 1, what does that mean? Actually, let me go back. I'll just ask that without all this. If your K is greater than 1, what does it mean about the concentration of your products versus your reactants? Which number's on top? Products or reactants? Okay, so K is P over R, products over reactants, right? So if I have a number greater than 1, then which number is bigger, P or R? You have more product. P is greater. If I have a number bigger than 1, that means I have a big top number, okay, and a smaller bottom number. Good. So when we say right to left, right is always product. Left is always reactant. Okay? So product is to your right, and reactant is to the left of the reaction. So that's how we describe it. Where does the equilibrium lie? It lies to the right, because my K is big. I have a big K. Okay? What if it is less than 1? What does that tell me? That I have more reactant, right? I have a big bottom number. My bottom number is bigger than my top number. So I must have more reactant, therefore I have a number less than 1. Okay? So that's what my K is telling me. So hopefully we've dispelled the myth that equilibrium means equal concentrations on each side of the reaction. That is not true. Okay? It means the rates of those reactions are equal. Okay? The forward and reverse rate are going at the same speed, and these are being held constant. These concentrations are being held constant. Okay, so homogeneous equilibrium just means you have everything in the same phase. Gas phases, okay? For gas phase equilibrium, you can actually use a different equilibrium expression for pressure, okay? Because the first one is in concentration, the Kc we call it. A Kc is a equilibrium constant in concentration units. Well, I shouldn't say units because your K is actually unitless. You don't use any units on your K. But your Kc would be derived by concentration, whereas a Kp would be derived from pressures. Okay? Atmospheric pressures directly. You could use it and you could still find your Kp, your equilibrium constant in pressure, okay, derived from pressure units. Now, a Kc and a Kp do not equal each other. So if I find the Kp, I can't assume that it's the Kc. They're not equal. It's just that would be my constant if I was looking at it in pressure units, or my constant if I was looking at it in concentration units. Okay? But they would be different. Now, there is a way that I can derive the Kc from the Kp. Okay? I can calculate what my Kp is by this equation. right here. So if I was given a Kp and I need to convert it to a Kc, this is how I would do it. Or if I was given a Kc and I need to put it into Kp, I would use this equation. Okay, let's see. Right here, this delta N stands for the number of moles of gas product minus the moles of reactant. Products minus reactants. How many moles of gas do I have on this side of the reaction, on my product side? 2. How many on my reactant side? 2 minus 1. That's what delta N would be here. Okay? It would be 2 minus 1 in this case. For other reactions, it would be very different. Okay? Okay. Okay, so here's an example of an equilibrium expression written in concentration units, a Kc, for this reaction, which is of acetic acid vinegar. Okay, vinegar plus water in equilibrium with acetate plus acid, H3O plus or H plus, however you want to say it. Okay. So I want to write the equilibrium equation here for my Kc. Products over reactants. There are no coefficients, right? No coefficients, so I don't need to raise anything to any orders. So I can just simply say the concentration of acetate times the concentration of H plus divided by the concentration of CH3COOH, or acetic acid, divided by the concentration of H2O. However, there's one thing that I need to change here. Okay? Can the concentration of water actually change? If it's in water, and I make more water, have I changed the concentration of water? It's a liquid. It's a pure substance. Okay? These other things are aqueous. You see how they're aqueous? That means they're dissolved into water. I can change their concentrations within the water, but I can't change the concentration of water within itself, right? So guess what? I don't include it in my equilibrium expression because it's a liquid. So if it's a liquid, I leave it off, okay? It does not get included, so I will rewrite it as this. CH3COO minus times H plus divided by CH3COOH.
All liquids?
All liquids.
All liquids.
All liquids because they don't change concentrations. Liquids don't. So if a liquid, a pure liquid, is part of your equation, you leave it off. Because when we're looking at equilibrium, all we're looking at is changes in concentration. Are they concentration amounts, okay? And the liquid is not going to. It's going to remain constant. Something like 55.5 molar, something like that. It's just always going to be that. So it's just, we leave it off. Okay? The same thing would be true if it was, they're not showing it here, but if it was a solid, something that it was a solid. So if I react something as a solid with something else, like a gas, that solid is not included in the equilibrium expression because the solid also doesn't change concentration. If I have 50 grams of it or 10 grams of it, the concentration is the same, right, between those 50 grams and that 10 grams. It's a solid piece of whatever, substance, okay? And so, same thing. If it's liquid or solid, I don't include it. I leave it off.
If it was a solid, wouldn't it not be a homogeneous equilibrium? Like, wouldn't they consider it, I think I read like a heterogeneous?
Yeah, that would be heterogeneous. Yeah, that's true. Okay? All right, the equilibrium concentration, and I think we're going to look at heterogeneous in a second, but that's right. Okay, if you have different phases, it'll be heterogeneous. Okay? The equilibrium concentration for the reaction between carbon monoxide and and molecular chlorine to form COCl2, okay, at 74 degrees Celsius are, and here's the equilibrium concentrations. Calculate the equilibrium constant Kc and Kp. Okay, so I need a reaction for this. Carbon monoxide plus chlorine produces COCl2. And it's balanced. Okay, it's pretty easy. All right. So it's all just 1 to 1 to 1. Okay, and this is going to be a gas. This is gas, and this is a gas. Okay. So my Kc is equal to the concentration of COCl2 divided by the concentration of CO times the concentration of Cl2. And then I just simply have to put my numbers in. Okay. So 0.14 divided by 0.012 divided by 0.054, what do we find? 2, say it louder.
216.
216. Okay? So 216 is my Kc. Well, I want to calculate my Kp from that. Okay, so the K, oops, that's right. I don't want to get it wrong. Oh, hold up right here.
R is that? Or 0 reactants?
Okay, so I want to use this equation. How many moles of gas do I have on the product side?
1.
How many on the reactant side?
2.
Okay, so it's 1 minus 2. Okay, so this will be to the negative 1, or the reciprocal of RT.
Wait, I'm sorry, is the delta N, is it products to reactants?
Products minus reactants. Products minus reactants.
Kelvin?
Yes, because my R, 0.0821, is in liter atmosphere Kelvin moles. Okay?
For the RT, you said was -1, correct?
To the negative, delta N is -1.
Okay, the RT's not.
No, you need to find out what that is by taking 74 degrees Celsius, convert it to Kelvin, multiply it by 0.0821, okay? Find out that number and then take the reciprocal of it. And you know your Kc is 216. That'll go right here, and that'll be easy to calculate your Kp then, okay? There are no, it's unitless. We don't have units on case on these equilibrium constants. They'll be unitless. Yep. Mm-hmm. Oh, okay, guys, we're done. Sorry. 7.58. Okay. Oops. Okay.